Alright, calculus, we are looking at in the section 21, this indefinite integration. We're going to be looking at a phrase called anti-differentiation, or antiderivatives, things that we're looking through. But before we get to that, we just want to talk about this idea of inverse processes and inverse objects. So let's start with just a few things that you guys are familiar with. The first one is we have this number 5. And what's its inverse? Well, there's actually a couple of options. Some people will say -5 would be its inverse, but you could also say 1 over 5, because it depends on if you're adding, subtracting, or multiplying, dividing. Similarly, for 1/3, it'd be the same kind of idea. If we got -1/3 or 3. The other one's a little more straightforward. What's the inverse of a boy? Most would say girl. What's the inverse of a dog? They would say a cat, maybe. And a lot of times, like, what's the inverse of cold? The inverse of cold is hot. Let's put all those three together, or a couple of those together. And if we have a hot dog, what's the inverse? I know some people are thinking hamburger, taco. But I'm going to steal this from my students in the class. They had said cold cat. I thought that was pretty clever. So this idea is just trying to get your brain to think of things in a reverse order or inverse order. So let's look at these processes and work them backwards the same way. So sit down would be, the inverse would be stand. Get dressed, well, the inverse of that would be disrobe or get undressed. Take a book home. This is open to interpretation here. Maybe we return it, or maybe we leave it. Either way. Okay, get wet or dry off. Go to sleep, wake up. All those kind of words. We get the idea. You do it one way, you do it backwards. You do the opposite of what you were doing before. So now what we want to look at is how that applies to the processes that what we were doing in math. So let's start out with algebra. This is going to be algebra here for a second. So a function. Let's say I have x plus 5. What's the inverse of that? Well, it's just going to be -5. Because if I plug this into the other the x minus 5, if I plug that into the other one, then I'd get just x, or 0. So that's what we have. This next one, let's say we had like 3x. Well, what if we were to say x over 3? That would be the opposite of 3 times x, would be x divided by 3. Okay, let's get a little bit more complex here. How about the square root of x? Well, the opposite of square root is going to be x squared, or the inverse of square root of x. There's other ones that we can do. We can do some trig, maybe. How about sine of x? Now this is a little tricky because a lot of people think sine, they think opposite or something different. They want to say cosine, but it's not. It's actually sine inverse, or sometimes called arc sine of x. Okay, now you could go on and on and on. We have, e to the x, and the opposite of that is the natural log of x, the inverse operation there. There's a lot of different versions of this. But now as we're getting closer to what we've been doing in calculus, let's talk about derivatives. We know that if we were to take the derivative of y equals x cubed, it would be 3x squared. So it makes sense to say that an antiderivative of 3x squared is x cubed. Now this is interesting. It's like going backwards, so it's backwards derivative. It's a back derivative. That's essentially what we're doing. So let's look at that even more closely. Something big is, we can't say it's the antiderivative, because when we go backwards, we don't know all the information about where we started. For example, when we looked at that example with x cubed. For the x cubed piece, we know the derivative is 3x squared, but if we took the derivative of x cubed plus 2, x cubed minus 5, x cubed plus 6 pi, all these constant terms go to 0, so we don't know if they're there or not. So that means when we take the antiderivative, we have to say that it's going to be the antiderivative plus c. We need that constant tagged on to there. Some constant. So if the derivative of 4x is 4, then the antiderivative of 4 is 4x plus some constant, because there could be a constant there that we don't. Let's go ahead and kind of get in some practice here, or some rules. You know, our differentiation formulas. If a constant goes to 0, then a 0 is going to go to a constant. That's kind of what we just talked about. If we take the derivative of a constant times x, then we get just a constant. So going backwards, the antiderivative of just a constant, we're going to have that constant times x to the first power. Similarly, the way that a constant kind of tags along on the outside, where it can be factored out, it can be factored out and tag along to the antiderivative as well. So we can factor out constants. Splitting it up into individual terms and adding and subtracting works the same for antiderivatives as it does for derivatives. This last one, so I'm going to cover up this piece here for a second. What do we do when we take the derivative of something to a power n? Well, if we have x to the n, the first thing we're going to do is drop that in. So we're going to drop the n, drop the power, and multiply. The second thing that we do is then we also say it's going to be subtracting 1 from the top. So we're going to subtract 1 from the power. Okay, so now that we've done that, let's think about doing this backwards. Instead of subtracting 1 from the power last, we're going to add 1 to power first. And then second, we're going to not multiply out front, we're going to divide by n plus 1. That new power, the adding 1 to the power is going to be up there. So now let's look at what this formula is. So the general idea, you add 1 to the power, then you divide by that n plus 1, and of course we always have this plus c. So here we have a 7. We could factor out this 7. It would be the integral times dx, or just the integral of k is going to become kx. So that's 7x. But we always got to remember the plus c. The next one, I have x to the n. So that's going to become x to the n plus 1 over n plus 1. So this 5 is going to become a 6. X to the 6th over 6, and then plus c. The next one, very similar, it's just a slightly larger number. 12 is going to become 13. We divide by that 13 as well, and then we have plus c. So how am I getting these numbers? I'm adding 1 to the power. For this next one, notice that I just have multiple terms, adding or subtracting. So I'm going to treat them individually. I'm going to do the first one. X to the 4th becomes x to the 5th over 5. For the second one, this x squared is going to become x to the 3rd, but now I've got to divide by that 3 as well. And it doesn't matter if you do one term, multiple terms, one side of an equation, both sides of an equation, you're going to always have plus a constant. Alright, now for this next one, same thing, 3 terms. T cubed, the 3 is going to become a 4. So we to the 4th power and divide by 4. T to the 1st power is going to become t squared over 2. And the 1 is just going to become a t. And we have a plus c. For this next one, we got a little bit of a combination. We have a constant and x to the n. Well, that constant we know is just going to factor out and then be tagging along. This x to the third power, that's going to become x to the fourth over 4, and of course plus c. The general idea is you kind of follow all the same rules at the same time, but you treat each one as an individual term as much as possible. And so these constants aren't going to be for all of them, just for that individual term. So the 2 gets factored out, but it's only used for this term. So we're going to have x squared changing into x cubed over 3. The second one, we have the 7 factored out. Becomes 7x to the second over 2. And the last term is minus 8x. And of course, plus a constant. For number 8, I see 3 constants. In fact, they're all fractions. So I'm going to go ahead and fill those in. 3/4, and then I got plus 5/3 and minus 1/2. This divide by 2 is the same as minus 1/2. So I'm just going to fill in the parts that have the x to a power. X to the 5th, that would become x to the 6th over 6. X squared would become x cubed over 3. And this last one, x to the 1st, becomes x squared over 2. Now I still haven't really simplified this one. I haven't really worked on simplifying any yet because I haven't really had to. This one we could if we wanted, and you would need to for a multiple choice type question. 3 and 6 would simplify to 1/2. And then we can start combining the products in the denominators. So we would have x to the 6th over 18 plus 5x cubed over 9 minus x squared over 4 plus c. Remember, if the pace is too quick at any time, go ahead and pause, return it back, take another look at it. All right, for this next one, we see multiple letters, but really only one variable. We have x as our variable, but this pi here and this pi here are constants. So we're going to treat them like constants. So the pi is just a constant that could be factored out, and it tags along. So we'll have the pi times, now the x is going to become x squared over 2. 1 over pi is really a constant, so I'm going to put 1 over pi here. But the antiderivative of a constant winds up having an x to the 1st, or a variable to the 1st power. Then of course, plus c. Again, a little bit of simplifying and rewriting you can do, but not really necessary. So let's keep moving through these examples. Okay, now we have some algebraic manipulation we need to do before we can process through the antiderivative. For each one of these, we want them to be x to the n and maybe a constant out front. Sometimes they'll have it and sometimes they won't. So let's look at the first one. That's the same as writing the integral of x to the negative 2 dx. That means that I'm just going to add 1 to that negative 2. So negative 2 plus 1 is negative 1. And then I'm going to divide by that as well. Again, we could simplify. We would get negative 1 over x, because x to the negative 1 means it just goes down to the denominator, plus c. For this next one, let's do some algebra first. We're going to bring up both of these denominators. That means I'll have 4x to the negative 3 and minus 5x to the negative 4 dx. So when I take the antiderivative of each of those terms, I'll have a 4 as my constant that's factored out. X to the negative 3, when I add 1, becomes x to the negative 2 over negative 2. Minus 5, and then we got x to the negative 4. It's going to turn into negative 3 for a power, and we divide by that number as well. Now, can we simplify this? Of course. You can always do algebra. We don't need to, but we can. 4 over negative 2 is really going to be negative 2, and x to the negative 2 is over x squared. Negative 5 divided by negative 3 is really positive 5/3. and the x to the negative 3 goes to the denominator as well. So if you had to remove negative exponents and duplicate signs, negative, negative kind of thing, this is what you would get. Let's do the next one. We'll do it in purple. Now, when we've dealt with square roots in the past, it's often easier to do derivatives if we change it to 1/2. Let's see if that helps us here. In fact, it does. Just because it's a fraction doesn't mean that we can't add 1 to it. A fraction can be added to the same way that an integer or a real number of any kind can be added. So let's do that. 1/2 plus 1, that's going to be 3/2. So x to the 3/2 over 3/2. We'll come back to that 3/2 in the denominator in a second here. Don't forget the plus c is your constant on the end. So when you have a denominator with a fraction in it, of course you can leave it, but if you did want to simplify and kind of get rid of the complex fraction, meaning that there's a fraction within a fraction, we need to flip and multiply. So we're going to flip this and multiply it. It would become 2/3 x to the 3/2 plus c. Easy peasy. So let's do these next three here. Let's start out with, how about back to black? Okay, so we got cubed root of y and fourth root of y. And now these are in terms of y. That's kind of something new. I know that we dealt with a t before, but really this d whatever, it doesn't really matter as long as that y and these y's are all the same variable. So if this was x, 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 we could do that. If it was z, 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 t, 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 w, 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 it doesn't really matter. It just matters that they're the same. Let's start though by translating this with some different algebra here. We're going to have 2y to the 1/3 minus 4y to the 1/4. Again, fractions, but we can deal with those. Just add one like you normally would. So this is going to become 2y to the, well, what's 1/3 plus 1? That would be 4/3. I'm also going to divide by that 4/3. Next we have 4y to the 5/4, because that's what 1/4 plus 1 is. Let's make this a little cleaner here. Over 5/4 plus c. Now again, if you wanted to do the algebra to simplify this, you can flip these denominators up and multiply them. That would give me 3/4 times 2y to the 4/3 minus 4/5 times 5y to the 5/4 plus c, of course. So this 4 and 2 would simplify. We'd have 3y to the 4/3 divided by... Alright guys, sorry for that interruption, but I went ahead and solved the problem out for you. Just had to pause it and someone walk in the room here. But anyways, so that's what we got so far. Let's keep on moving with this manipulation before we do the integration. So for this first one, I see a square root in the denominator. That tells me that I can do two things. It's kind of like a combo play. That means we're going to have x to the 1/2, but not just x to the 1/2, x to the negative 1/2 for that first term. For the second term, we'll still keep it as x to the 2/3. So now working through this, if we add 1 to each of those powers, the first one's going to become x to the 1/2, because negative 1/2 plus 1 is 1/2. And then we have 2/3 plus 1 is going to become 5/3. We divide by that 5/3. Of course, we have the plus c. If you did want to do some simplifying, you could say x to the 1/2. Whoops, not plus. Minus 3/5 x to the 5/3 plus c. For the last one, I know it's a little bit shaky, kind of hard to read here, but it does say x to the pi. Pi is a number, just like all the others. It's just a number that we don't know how to write out without approximating. So then let's treat it like a number. Which means this first term is just going to become x to the pi plus 1 over pi plus 1. Similarly, square root of pi is just a constant, so we're going to treat it like a constant. Just kind of tags along. It gets factored out and then comes on back. But the antiderivative of with a constant there means it's going to become x. And of course we have plus c. All right, we're part 1. We only got here 3 in fact. And then we'll move on to part 2, dealing with the trig, and part 3, dealing with differential equations. So let's look at part 1 here, or the end of part 1. This is not easy, but we've learned that sometimes it's easier to deal with terms, with derivatives, when it's individual terms, not like a complex one term with multiple layers. Because right here I see layers. I see an inside layer and an outside layer. So what I want to do then is multiply it out. So let's go to multiply that out. 2x minus 3 times 2x minus 3 is going to give me 4x squared minus 6x minus 6x plus 9. So in a version down here, I'll write 4x squared minus 12x plus 9. Now I got 3 individual terms. I can do each one separate. Let's go ahead and do that. The antiderivative of 4x squared, well, the 4 is a constant. It gets factored out. It can be dealt with just by tagging it along. X squared becomes x cubed over 3. The next one says minus 12x. Well, I have the minus 12 for the constant. X to the first is going to become x squared over 2. And the 9 is just going to become 9x. Of course, what's on the end? Plus c. We could simplify this 12 and 2 to be a 6 and 1. That's about it that we could do to simplify, but that definitely helps. The second one here is we have lots of numerators, one denominator. So we're going to distribute. In the same way that if this said x to the fourth times x squared plus 3x plus 1, and I would distribute to separate the terms, this one up here is saying 1 over x to the fourth times x squared plus 3x plus 1. So that's really, so if I distribute this then, we're going to get x squared over x to the fourth, 3x over x to the fourth. Let's see what's here, x to the fourth, plus 1 over x to the fourth. Now we're getting really close to having this completely ready to integrate, but let's do one more thing. Let's try and get this as some power x to the n. Well, x squared over x to the fourth would give me 1 over x squared, or I could just write x to the negative 2. 3x over x to the fourth would really give me 3 over x cubed, or 3x to the negative 3. 1 over x to the fourth is just x to the negative 4. So there's my 3 terms. Let's integrate or anti-differentiate each one. So x to the negative 2, we add 1 to the negative 2, we get x to the negative 1 over negative 1. For the next one, we have the 3, which is a constant, so we can factor it out and tag it along. X to the negative 3 is going to become x to the negative 2 over negative 2. Now the last one, we have x to the negative 4. So if we add 1 to that, it's going to become x to the negative 3 over negative 3 plus c. Now for this last one, I'm actually going to do it on the next page. We're going to do a combination of the two things that we just did. First, we're going to multiply out, and then we're going to split into individual fractions. Let's do it. So the first idea is we need to multiply out this top piece here. We have 2x minus 5 times 3x plus 2. So we have 2x times 3x. That would be 6x squared. Negative 5 times 3x is going to be minus 15x. 2x times 2 is 4x. And then the last one is negative 10. So if I combine all these together, that would give me the top piece is equal to 6x squared minus 11x minus 10. So we have all of that over square root of x, or x to the 1/2. So I'm going to simplify this by separating it into multiple terms. We'll have 6x squared over x to the 1/2, 11x to the first over x to the 1/2, and minus 10 over x to the 1/2. This 11x, that's also a minus as well. Okay, so now we're at this point, we can start simplifying each term by combining those x's in the numerator and denominator, just making 1 to a power in the numerator. So this first one would be 6x to the 2 minus 1/2 is 3/2. The next one will be minus 11x to the 1/2. For the last one, we have minus 10. That x to the 1/2 in the denominator becomes x to the negative 1/2 in the numerator. Now we are finally ready to integrate. For the first one, we take the power, we add 1, we'll have 6x to the 5/2 over 5/2. The next one is going to be minus 11x to the 1/2 plus 1 is 3/2, and we say over 3/2. For the last one, we take negative 1/2, add 1, we got minus 10x to the 1/2 over 1/2, and then of course plus c. Could we simplify? Yes. But am I done? Yes. So are you. See you in part 2.